So in this session we are going to see about the forced vibration with rotating and reciprocating unbalance, then forced vibration due to the excitation of the support, then about what is vibration isolation, and what is meant by transmissibility and the different types of the transmissibility. So these are the topics we are going to cover in this session. So now we are going to see about the forced vibration due to the rotating and that is reciprocating unbalance. That is the forcing caused by the unbalance. So generally all the rotating and reciprocating machineries like motor or turbine or any engine have some amount of unbalanced force. So already in the third unit, second unit, we have studied about the unbalanced forces. So if all the machineries have some unbalanced, even though we have balanced all the machines by our method of balancing, even though balancing is done, there is some little amount of unbalanced force is left in them. So this small unbalanced force produces a exciting force in the machine, that is a vibration. So in the figure you can see that there is a rotating and reciprocating machine. So in this machine you can see that this is a rotary machine. So here the rotary machine, it may be balanced by a spring and a damper. So the spring has a stiffness K and a damper has a coefficient of C. It may be balanced. It may be balanced with a foundation. So now this rotating mass, the total rotating mass, the mass of this is M, taken as M, capital M. And small m is the unbalanced mass. So the unbalanced mass is small m, and the distance between the center and this distance is unbalanced mass is taken as E, that is the eccentricity. So it is rotating. The mass, the unbalanced mass is having a radius of E, and it's rotating in the anti-clockwise direction. So the angle is omega. It is rotating with an angular velocity of omega in the anti-clockwise direction. So due to this unbalanced mass, there is some displacement. So this due to this unbalanced mass, there is some displacement because a centrifugal force. So due to this unbalanced mass, a centrifugal force is acting outwards. So due to the centrifugal force, there is some vibration in the machine, and hence it is a displacement taking place in the rotary machine. So here also we can see that is a reciprocating machine. So here also we are taking the rotary part. So same as we have seen here, the piston is here, the crank is here. So the piston mass is considered as it is placed at the crank end, and so the unbalanced mass is rotating with an radius E, eccentricity, and angular velocity omega in the anti-clockwise direction. So here also we have considered the eccentricity. The length of the eccentricity is taken as half of the crank length. So if the crank length from here to here it is L means, then we take that the eccentricity as L by 2. So that is considered, assumed here. So here we are assuming two things. One is the piston mass is placed on the crank end, and the crank length is half of the stroke length. So this is a crank length. So here we are taking the eccentricity as a crank length. So the crank length is half of the stroke length, that is E is equal to L by 2. So these two assumptions we are taking in this reciprocating machine. So when we consider the equivalent system, we consider, see, you can see the both the rotary part is same as the shown in this equivalent system. So instead of this rotary and reciprocating system, we have considered a mathematical model, that is a equivalent system is considered for our solution. For a problem solution, we are considering a equivalent system instead of considering a rotary or reciprocating machine. So this is the equivalent system. The same pattern is shown here, that is the entire mass is taken as capital M, and the unbalanced mass is taken as small m. So it is having an eccentricity length of E and rotating with an angular velocity omega. So due to this unbalanced force, and centrifugal force is acting outwards, and due to this there is some excitation or vibration in the system, and hence since there is a vibration, the system has a displacement of x in the machine. So it is the system is fixed with a foundation with a spring and a damping system. So this is a system, that is the equivalent system about the machine. So the same is shown in this figure 1 also. So the equilibrium position, so the same total mass is mass of the system is machine is capital M, and the unbalanced mass is small m, and the eccentricity is small e. Then the stiffness of the spring is K, and the damper coefficient is C, and this spring and damper is fixed to the ground, is fitted with the ground. So the same what we have assumed as a mathematical model is shown here. So here this is taken as a mean position of the system. So now you can see that. So this is the displacement. So we know that the unbalanced mass is rotating at an anti-clockwise direction. So the displacement, so due to this unbalanced mass, there will be some disturbance in the system. So there will be some excitations. So the machine is displaced to a distance of x in this direction, in the vertical direction. So the excitation will be in the vertical direction, that is the displacement will be in the vertical direction. So this is the displacement. So the displacement is shown here. So now, so we see that the mass is now displaced to the distance x. So that is this mass is due to the, why this displacement is there? So this displacement is due to the net mass. So what is the net mass? It is capital M minus small m. So due to this net mass, there is the displacement x. That is the displacement of the machine is due to the net mass. So what is the net mass? Capital M minus small m. So due to this net mass, here you can see that we have assumed the mass of the unbalanced mass is small m, the mass of the machine is capital M, and eccentricity is small e. Angular velocity of the rotor is omega, it is rotating at an angular velocity omega. The total engine mass, total mass of the engine is capital M. So the displacement of the machine due to the net mass capital M minus small m is x. So this is the displacement of the machine due to the mass capital M minus small m. So next we are going to find the velocity of the next mass. So velocity means we have to differentiate this with respect to time. So dx by dt. So this is denoted as a short form as x dot. Then acceleration of the net mass is dx dot by dt, that is x double dot. So next we are going to find the displacement of the mass. So now the unbalanced mass is start to rotate at an angular velocity omega, at an angle that is omega t for a time period of t. So it is moved to this distance. So now we are going to find the displacement, the total displacement of the mass. So the total displacement of the mass, so this is a mean position, initial position. So from here it is up to this distance now. So this distance is to be calculated. So this is x plus, so this vertical component is e sin omega t. So x plus e sin omega t is the displacement of the mass. So here you can see. So the displacement of the mass m is x plus e sin omega t. So x, the small distance is x plus e sin omega t. So next, if you want to find the velocity of the rotating mass, we have to differentiate this. So x, if we differentiate with respect to time, it is x dot plus e is a constant. E is a x crank radius, so eccentricity is a constant e. Then sin omega t. So omega into cos omega t. Differentiate this sin omega t. So omega into cos omega t. So then find the acceleration. So acceleration of the rotating mass. So x dot is here. So x double dot minus y minus, differentiation is cos is minus sin. So minus e omega square. Already known omega. After differentiation we will get omega. So omega square sin omega t. So this is the acceleration of the rotating mass. So next we are going to draw the free body diagram of the machine. So this is the entire mass of the machine, capital M, and this is the spring mass. So spring mass is written as kx. So it is acting downwards, and the damping, that force is acting downwards. So c dx by dt. So it is written as x dot. So here we know that the system, that machine is moving, the displacement of the machine is upwards. So the machine is moving upwards. So that means the inertia force is acting in the downward direction. So the inertia force due to the net mass of the machine is m minus m into d square x by dt square. So that is x double dot. Why we are taking m minus m? Because that unbalanced mass is within the mass, capital M only. So we have to minus that. So capital M minus m is the net mass. So into x double dot. Double dot means d square x by dt square. So then the mass of that unbalanced mass. So unbalanced mass is written as m into so the mass into acceleration. So acceleration means we have written in the previous step. So the formula for acceleration of the mass is x double dot minus e omega square sin omega t. So this is the acceleration of the mass. So we are writing this as, so multiplying m inside. So m x double dot minus m omega square e sin omega t. So we have written all the forces. So now we are going to apply the D'Alembert's principle. So D'Alembert's principle is summation of the inertia force and all the external forces are equal to 0. So first, so here you can see all the forces are downward direction. So according to our engineering mechanics, the downward forces are taken as negative and upward forces are taken as positive. But here we can see all the forces we have taken as only positive. So because for our problem calculation only, we have taken all are positive. So you can also take all the forces as negative and you can solve the problem. So now here it is taken as all are positive. So we are taking one more step. We can take all the negative sign, we can cancel, we can make it as positive. So next, so first force, this is the first inertia force. So m minus m into x double dot. This is the inertia force of the machine. So inertia force of the unbalanced mass, that is written as m x So m is taken as common, x double dot minus e omega square sin omega t plus the spring force is kx and the damping force is c x dot. So all the forces are given here. So from this I am taking that is equal to 0. So here we can solve this. So mx this is cancelled. So mx double dot then plus c x dot plus kx. So this is minus, no, so we can take to the other side. So this equation, this governing equation is called as the non-harmonic characteristic equation. So this is a non-harmonic characteristic equation. So already we have the equation of forced vibration, that is equal to f naught sin omega t. So both when we compare both the equations, so this part is equal, left side is equal and right side we can compare from this equation. So f naught is taken as m e omega square. So f naught is m e omega square from this two comparing equations. So but the actual practice, the value of the displacement is given by the particular integral only. So there is no value from the complementary function. Here we get only the value from the particular integral. From this particular integral only we get the value. So this is the final equation we have got from this, from solving the particular integral of this equation. So x is equal to m omega square e by root of, so full root of s minus m omega square the whole square plus c omega the whole square into cos omega t minus phi. When we solve this equation, the particular integral, when we solve, we get this equation. So this is x max, is written as x max. So the maximum value of the amplitude. So x max is the value of the amplitude of the vibration. So if they ask amplitude of vibration, we have to use this formula. So amplitude of vibration, when we get, when this value becomes the 1. So when it becomes 1, cos 0 is equal to 1. So at cos 0, so this value we get the maximum amplitude of vibration, or the, we can tell the displacement, maximum displacement. So while solving the problem, we need not use this formula. So the simplified formula we have to use this. So this m e, that part is taken to the next side. So x by m, small m e by capital M is equal to r square root of 1 minus r square the whole square plus 2 zeta into r. 2 zeta, zeta is the damping coefficient. So that is a factor, coefficient factor is, so damping factor is zeta. So 2 zeta r whole square. So we can use this formula instead of this formula. So where x is the amplitude, small m is the mass of the unbalanced mass, small mass. E is the eccentricity, capital M is the mass of the machine. So R is the frequency ratio. Okay, so using these values we can solve the problem. So the value phase angle, so the phase angle also can be written. Phase angle phi is equal to tan inverse 2 zeta r by 1 minus r square. So where r is equal to omega by omega n. Omega by omega n is r. So using that is a frequency ratio. R is a frequency ratio, omega by omega n. Using this formula we can solve the problem. So next we can see a problem. A vertical single stage air compressor having a mass of 500 kg is mounted on springs having stiffness of 1.96 into 10 power 5 Newton per meter. So this is a air compressor. That machine, total mass of the machine, capital M is 500, stiffness S is this much, and dashboards with the damping factor of 0.2. So damping factor means it is zeta 0.2. The rotating parts are completely balanced and the equivalent reciprocating parts weighs 20 kg. So small m is 20 kg. The stroke is 0.2. So the strength of the stroke is 0.2. So L is 0.2. So determine the dynamic amplitude of the vertical motion and the phase difference between the motion and the excitation force if the compressor is operated at 200 rpm. So we have to find the amplitude of the vertical motion and we have to find the angle, phase difference phi. So we saw the two formulas. So we have to find the amplitude and phase difference when the n is given as 200 rpm. So write the given datas. So using n, we have to find the omega. So omega is 2 pi n by 60. So this much radian per second. And omega n is root of s by m. So directly they won't give the natural frequency. We have to find the natural frequency by this formula, root of s by m. So stiffness, if in case of spring, we have to use only this formula. So spring, the value stiffness is given, small, that is m is 500. So this is for total the machine, no? So we have to take the capital M, entire machine. So 500 kg. So it is 19.8 radian per second. So the frequency ratio R is equal to omega by omega n. So omega is given, is calculated, and omega n is calculated. So R is 1.057. So next, eccentricity is stroke by 2. So stroke is 0.2. 0.2 by 2 is 0.1 meter. That is E is 0.1 meter. So we have calculated all the values. So from this we have to find the amplitude. So first, dynamic amplitude of the vertical motion is x max. So the formula I have written, x max by mu, that is small unit mass. This is total mass. This is unit mass, small mass, E by m. This formula is written. Substitute. So x we have to calculate. So 20 is small m, that E, then this is capital M. Then R is substituted, zeta is substituted. So the answer for the maximum amplitude is written 10.18 mm. So this is the maximum amplitude, or we can say the displacement also. So phase difference formula is phi is equal to tan inverse of 2 zeta r by 1 minus r square. So using this formula, you can find the phase lag or phase difference. Substitute for zeta and r. Now we can find the answer. So it is obtained as minus 74.35 degree. So since it is a minus value, we are adding, that is plus 180 degree. So that is tan inverse of minus 3.57. So that is tan inverse 105.64 degree. So tan 180 plus theta is equal to tan theta. So using this formula, we are putting the minus value to plus. Next we are going to see the topic of forced vibration due to the excitation of the support. So you are going to see the support motion. So here you can see there is a system. So here the system is supported at one end, and on the other end there is a mass. So there is a spring and damper. So this system can be called as a damped spring mass system. So in this damped spring mass system, we are going to consider the support motion. So since the mass is hanging from the support, so we consider that there is a displacement due to this mass. There is a displacement x which is acting downwards, which is the displacement is downwards. So also not only this displacement, but in many applications the external force is acting on the support also. So in many applications the excitation is applied through the base or the support instead of being applied to the mass. So here there is a external force, and due to this there is a displacement y. So that y is equal to y sin omega t. So So let the support or the base is excited by a regular sinusoidal motion, y equal to capital Y sin omega t. So it is moving with a sinusoidal motion. So that is given by this equation. So now we are going to discuss two different response of the system. One is the absolute response or absolute amplitude, and second one is the relative response or the relative amplitude. So first we have to understand what is meant by absolute response or amplitude and relative response or relative amplitude. So absolute response means, so here the mass, there is a mass. So if we consider x is the absolute motion of the mass, if x is considered as the absolute motion of the mass without considering this mass from the support, that displacement from the support. So if we are considering only the displacement of the mass, that is x alone if we consider, and if we do not consider the y, then it is called as the absolute response or absolute amplitude. So relative amplitude means if we consider this x with respect to, that is relative to y. So if x relative to y is considered, then it is called as the relative response. So this is about the two different response of the system. So here if the x is the absolute motion of the mass, then the equation of the motion can be written as follows. Here we consider all the forces acting, and we are considering the Newton's second law of motion. That is the acceleration, that is equal to the sum of the, that is the inertia force, and the sum of the all the external forces, it is equal to 0. So here this is the inertia force. So the displacement is downwards, that means the inertia force acts upwards. So what is inertia force? Mass into acceleration. Mass into acceleration is, displacement is x, so acceleration is d square x by dt square. So that is equal to the spring force. So it is upward force. So it is, so here you can see some types of isolation that is given in the machine. So here this is a machine. So this is the foundation. So the vibration which is transmitted from the machine, see it is there is a spring and damper provided. So all the vibrations cannot be transmitted to the foundation. So the foundation is protected by this system. So this is forced isolation. So here you can see the equipment. The equipment is protected with respect to some spring arrangement. So here the equipment is protected by this arrangement. So it is an example of a motion isolation. So the foundation, if it is protected, if it is to be protected, it is a force isolation, and if the equipment is to be protected, it is called as the motion isolation. Negative. So the value is minus s into the distance. So the distance from here to here is x minus y. So that is the spring force. Next one is the damp force. That is also upward force. So it is negative, taken as negative. So minus c into dx by dt minus dy by dt. Dx by dt minus dy by dt. So this we take this to the left hand side. So m d square x by dt square, we take this c dx by dt x terms to the left side. So plus sx equal to sy plus c dy by dt. So here we are going to substitute for y equal to capital Y sin omega t. So because here we have the value, so if we get the answer is So left hand side you keep as it is. So right hand side s into y, substitute y here. So y sin omega t plus c into y cos. So differentiate y. So differentiation, the y is constant, so y cos omega t into omega. So after substitution, after simplification, we can write this. So you can write m d square x by dt square plus c dx by dt plus sx equal to, take y as common. The simplification you can write s square plus c omega whole square into sin omega t plus alpha. So this alpha term, so why we have written the simplification, so that the simplification procedure is not important for us, so the answer is sufficient. So after the final simplification we get this answer. So here alpha is equal to tan inverse of c omega by s. So that is equal to tan inverse of 2 zeta omega by omega n. So this equal to 2 zeta omega by omega n. That is equal to tan inverse of 2 zeta r. So this is r, frequency ratio. So this is the solution. So the solution is same as that of the equation. So before it is the equation. So therefore the amplitude of vibration can be given as, so x max equal to y into root of s square plus c omega square by root of s minus m omega square the whole square plus c omega the whole square. So you have to study this formula. So this formula is for finding the that is the displacement or absolute amplitude of the system. So here this equation can also be written as x max. So this y you can take this side. So x max by y equal to root of. So if further simplification, we can get the formula. In terms of frequency ratio also we can write. So x max by y equal to root of 1 plus 2 zeta r the whole square by root of 1 minus r square the whole square plus 2 zeta r the whole square. So in terms of the frequency ratio, so this is the formula for finding the absolute amplitude. So you study this end formula. So derivation part, this is sufficient for us. So you have to keep the formula, you have to remember this formula for the problem solving. So next we can see the phase angle phi. So the phase angle phi, already we have seen this formula. So phi is equal to tan inverse of 2 zeta r by 1 minus r square. So this is the value for the absolute amplitude. So next, the relative amplitude. So already we have seen that the relative amplitude is the, so the response of the system, the relative to the moving system is called as the relative amplitude. That is the response of the entire system with respect to the relative to the moving system. That is the two displacements are there, x and y. So relative, the x relative to y should be taken. That is the relative amplitude. Absolute amplitude means if x alone is taken as the absolute mass, then it is absolute amplitude. So relative amplitude means this x along with the, that is relative to the displacement y is also considered. That is the relative amplitude. So here relative amplitude we are taking z equal to x minus y. So in absolute amplitude we are taking with respect to x, but relative amplitude we have to take with respect to z. So here we are taking z is equal to x minus y. So z is equal to x minus y, or we are going to substitute for x as y plus z. So in the similar equation, so in the absolute amplitude, in this equation, we are going to simplify. We are going to simplify the for y we are going to simplify as x x equal to y plus z. So this we have to simplify. So after simplification, we get this formula, that is m d square z by dt square plus c dz by dt plus sz equal to minus m d square y by dt square. So on that equation, if we simplify for x as y plus z and solving, we get this equation. So in this equation, we are going to substitute for y as capital Y sin omega t. So the d square y by dt square, if we differentiate, the y is constant, y into sin omega t. So 2 times we have to differentiate. So first it is cos omega t and the second time it is minus sin omega t. So minus sin omega t into, if we differentiate 2 times, you get omega square. So this is the answer. So m d square z by dt square plus c dz by dt plus sz. So here you can write minus m, already here one minus, so plus m y omega square sin omega t. So this is the formula. This is a characteristic equation. So this is a complementary function and this is the particular integral. So here we are neglecting the complementary function, and the maximum amplitude is obtained only by the particular integral, and this is the final formula for the relative amplitude. So the derivation is not important for us. So the answer is sufficient for solving the problem. So z by y equal to r square by root of 1 minus r square the whole square plus 2 zeta r the whole square, where r is equal to omega by omega n. So this is the formula, end formula for the relative amplitude. So relative amplitude, the value will be in terms of z, and for absolute amplitude, the value, the formula will be in terms of x. That is a difference. Next is the vibration isolation. So what is meant by vibration isolation? So the vibrations that are produced in the machines have some unbalanced forces. So even though if we balance all the forces, so some amount of forces will be remaining in the machine as unbalanced forces. So due to these unbalanced forces that are installed on the foundation, so the unbalanced machines are installed on a foundation, so the vibration that is caused in the machine will be transmitted to the foundation. So in order to prevent this vibration, or in order to minimize the transmission of the forces from the machine to the foundation, the machines are usually mounted on spring or damper or some other vibration isolating materials like rubber, cork or any spring. That is called as the vibration isolating materials. So these devices isolate the vibrations by absorbing some, that is the disturbance, and it allow only a fraction of it to the foundation. So it doesn't give the vibration, entire vibration to the foundation. It observes the isolating materials. The materials absorbs the vibrations and give only a little amount of the disturbances to the foundation. So that type of system is called as the vibration isolation. So here we use some different materials as a vibration isolating materials. So they are rubber, felt, cork and metallic springs. So here in the picture you can see this is a rubber, then this is a cork material, then this is the felt material, and this is a spring, metallic spring. So these materials can be used for absorbing the vibrations from the machine to the foundation. So here we can see clearly about the vibration isolation and the types of vibration isolation. So the vibration isolation is called as the process of reducing the transmitted force to the foundation by using isolating materials. So the transmitted force from the machine to the foundation is to be reduced. That process is called as the vibration isolation. So it is done by some of the isolating materials. So there are two different types of vibration isolation. That is, one is the force isolation, another one is the displacement isolation. So in the force isolation, here you can see this is the system, machine. You consider this as a system, machine. So it is giving the force, it is giving the vibration to the foundation. So the force from the machine is transmitted to the foundation through the spring and damper. So here there is a spring and damper. So to observe the or to deliver the vibration, it is present in the system. So the vibration which is transferred from the system or machine to the foundation is to be protected. So here the foundation has to be protected. So for protecting the foundation, we have to provide some isolating materials here in the before the foundation to absorb the force given from the, this is a source, from the machine to the foundation. So here the foundation has to be prevented. So this type of isolation is called as the force isolation. So the foundation, in order to protect the foundation, we are using the isolating materials here. So that type of isolation is called as the force isolation. So here you can see, so this is the source machine. So this is the isolator, that is spring and damper. So this is the foundation, that is a source isolation. So here the excitation force which is given from the source is in the form of the sine wave, and here this force is transmitted to the foundation. So the excitation force, so how much of the excitation force is transmitted to the foundation? So that is calculated, that is determined by means of this method, force isolation. So here all the excitation force is not transmitted to the foundation, only little force is transmitted. So we are going to calculate, we can calculate how much force is transmitted to the foundation. So that method is called as the force isolation. So next is the motion isolation or displacement isolation. So here what we consider means, so this is the source here, this is the force applied displacement here. So we receive the vibration, or the disturbance from this foundation. So from this foundation, so here it is passed, the vibration or force is passed through the spring and damper to the system. So here this equipment has to be protected. So that type of isolation is called as the motion isolation. So for example, for force isolation we can consider a railway track. So there a train is passing in the railway track. So if a house is nearby the railway track, the house, in the house we experience the vibration when the train is passing through the track. The vibration is felt in the house. So we cannot change the house to somewhere. Okay, so what we have to do? So we are having so many things in the house. So due to the vibration, the things, the TV or the equipments may be damaged due to this vibration. So we have to protect the equipments. So that type of isolation is called as the motion isolation. So the equipments have to be protected from the vibration. So that is called as the motion isolation. So here also you can see this is the receiver. So receiver isolation. So from here the force has to be passed to the system. So this is the equipment. So from here the vibration or the disturbance is passed through the equipment. So this equipment has to be protected. So here we should have any isolating material for protecting the equipment. So here we have to determine so how much vibration is responded, that is for the excited motion, how much vibration is in the responded motion. So that type of response is calculated or determined by this type of isolation, that is motion isolation. So force isolation and motion isolation. So the force isolation is the unbalanced machines are isolated from their foundations so that there should not be any damage to the machines and foundations. So the foundations has to be protected. So there should not be any damage to the machine as well as to the foundation. So the foundation has to be protected from the vibration. That is called as the force isolation. Motion isolation is safeguarding the receiver from vibrating sources. So the receiver is safeguarded from the vibrating sources. That is called as the motion isolation. So here a good example for motion isolation is safeguarding a computer monitor from the vibrating body. So if there is a continuous vibration in the computer monitor, the computer monitor may undergo a failure. So we have to protect the monitor from the vibrating body. That is called as the motion isolation. So here there is one statement given, that is the lesser the force of motion transmitted to the support, greater is the isolation. So if the isolation function, if it is to be greater or if it is done in a good manner, that means when it is done in a good manner, only when the transmitted force is very less. So if the very less force is transmitted to the support, that means the isolation will be greater. That is the statement which is given in the vibration isolation. So next topic is the transmissibility. So transmissibility is the measure of the effectiveness of the vibration isolating material. So or we can say that it is a reduction of the transmitted force afforded by an isolator. So that is so here there is a source of vibration. So here there is a receiver. So in between the source and the receiver there is a vibration isolator. So from the source, so it depends upon the vibration, depends upon the what force we are applying to the source. So this applied force is passed through the spring. This is a vibration isolator. So through this vibration isolator, it is passed through the foundation. So all the vibration forces is not transmitted to the foundation. So the less force of vibration only it is transmitted. So if only lesser force is transmitted, it is a good isolator. If it is transmitting more forces to the foundation, then it is called as the bad isolator. So for the property of a good isolator, it is to transmit only the lesser force of vibration to the foundation. So that is the principle. So already we have seen about the force isolation. So the same principle here we are seeing that. So from the source, so the applied force is transmitted to the foundation. So this ratio of this vibration transmitted is called as the force transmissibility. So force transmissibility is defined as the ratio of the force transmitted from the source, from the force applied on the system to the foundation. So that ratio is called as the transmissibility. So force transmissibility eta equal to force transmitted to the foundation. So to the foundation. So this foundation transmitted force is Ft. So the force applied on the system is F0, initial force, applied force. So that ratio is called as the force transmissibility. So similarly, the motion isolation we have studied, the same principle is applied for motion transmissibility. So here so this is the source. So from here the force it is transmitted, so in this direction, upward direction, to the device. So through the spring and the damper, this is the vibration isolators. Through this the vibration or force is applied, is passed. So this ratio is called as the motion transmissibility. That is the absolute amplitude of the mass. So this is the absolute amplitude of the mass divided by amplitude of the base excitation. So this ratio, how much is received from the device, from the source, how much vibration is received to the source. So that ratio is called as the motion transmissibility. So it is written as eta A equal to x max by y equal to Ft by F0. So Ft is the device, the transmitted displacement to the device, and F0 is the source of vibration, it is F0 from the base. So this ratio is called as the motion transmissibility. So here there are some formulas for force transmissibility and motion transmissibility. So the formula is enough for us, the derivation is not needed. So the ratio is force transmissibility is equal to force transmitted to the foundation, that is Ft by force applied on the system F0. So Ft by F0 equal to root of 1 plus 2 zeta r the whole square by 1 minus r square the whole square plus 2 zeta r the whole square. So already this formula we have studied in the earlier calculations. It is x max. So that formula only this. So this formula is important for us to solve the problem based on the force transmissibility. So here this we are going to from this formula we are going to write 4 results based on the frequency. So at resonance means the R is equal to 1. That is a frequency ratio R is equal to 1. When R is equal to 1, when omega is equal to omega n, R will be equal to 1. So the transmissibility becomes, so if we take R equal to 1 at resonance, so the formula becomes like this, root of 1 plus 2 zeta whole square by 2 zeta. When zeta is equal to 0, that is if there is no damping, then the damping coefficient will be 0. That means what happens to the transmissibility? It is plus or minus 1 by 1 minus r square. So when r, that is the frequency ratio, is less than 1, that means eta equal to 1 by 1 minus r square. and when the frequency ratio R is greater than 1, then eta is equal to 1 by R square minus 1. So these are the 4 results we are studying from this formula, force transmissibility. So the phase angle is equal to the same formula only, tan inverse 2 zeta r by 1 minus r square. So the phase lag is also calculated, phi minus alpha equal to tan inverse 2 zeta r by 1 minus r square minus tan inverse 2 zeta r. So this is a formula for force transmissibility. Next, similarly, the formula for motion transmissibility is, so the same formula only for motion transmissibility. So eta A equal to x max by y, the same absolute amplitude of the mass, that is the mass, this is the device, divided by the base excitation, that is the source. So that ratio is the motion transmissibility. So the formula is Ft by F naught equal to root of 1 plus 2 zeta r the whole square by 1 minus r square the whole square plus 2 zeta r the whole square. The same formula for both force transmissibility and motion transmissibility. So using this we can solve a problem. So here there is a transmissibility with a frequency ratio. So from this graph we can have a conclusion that when r is less than root 2, that means the eta is more than 1 for all values of zeta. So when r is greater than root 2, that means eta is less than 1, and that means the transmitted force is always less than the exciting force. When r is equal to root 2, then eta is equal to 1 for all values of zeta. That means the transmitted force is equal to exciting force. When r is equal to 1, that means the transmitted force is infinity. So if damping is used, the magnitude of the transmitted force can be reduced. So when r is greater than root 2, that means eta increases as the damping is increased. So this is a conclusion we get from the graph. So next we can see one problem. A machine 100 kg has a 20 kg rotor with a 0.5 mm eccentricity. The mounting springs have S equal to 85 into 10 power 3 Newton meter. So the given data's mass is given. So this is a unit mass, small mass, and eccentricity is given, and the stiffness of the spring is given. So the damping ratio is given, that is eta is given, zeta is given. The operating speed is n is given, and the unit is constrained to move vertically. So the motion is vertical motion. Find dynamic amplitude of the machine and the force transmitted to the supports. So the dynamic amplitude is x max. So the formula is we know that x max formula. So using that x max you can find the amplitude and the transmitted force. So force transmitted to the supports formula also we know. So force transmissibility formula. So using that we can solve this problem. So here first we have to find the speed n. We have to convert to omega. Omega is equal to 2 pi n by 60. So find the omega value. Next, using omega, then after finding omega, then find omega n. So omega n is root of s by m. So if the spring stiffness is given, then the natural frequency can be calculated by this formula, root of s by m. So find this much. So r is omega by omega n. Then f naught equal to m u omega square e. So from the derivation we know this part. So every values are given, so you can find f naught. So first is you have to find the dynamic amplitude of the machine. The formula is x max equal to f naught by s by root of 1 minus r square the whole square plus 2 zeta r the whole square. So f naught we have calculated, s we know, r we know, then zeta also we know. So the simplify all the values and find the answer. So x max that is the maximum amplitude, or we can say the displacement. It is 0.127 mm. So next part we have to find the force transmissibility. That is the force transmitted to the supports is eta equal to Ft by F naught. So Ft is the force transmissibility. F naught we know, zeta we know, R we know. So substitute this value and find the force transmissibility, that is Ft. So that is equal to 10.87 Newton. So with this fourth unit is completed. So thank you. We can see in the next session.